Today we are going to talk about how to analyze and predict the loss in contact force in plastic assemblies. Plastic material creep over the time and hence the interface gets loosened over a time and so on. Especially in the assemblies where it transmits some loads or torque, there should be a sufficient torque between the shaft and the plastic pulley interference. Otherwise, the joints start slipping once it exceeds a certain limit load. So it is important to design the interference fit such that at all the point of time, the torque that interference can take should be more than the torque flowing through the system. For today's example, let's take a typical assembly. There is a plastic pulley inserted over a steel shaft. We can assume that the steel shaft is relatively rigid compared to the plastic material property. So our objective here is to find how much torque this joint can stand. So when you are doing this process, if you want to understand the torque, basically there is a material here and there is an interference fit. Because of the interference fit, there is a contact pressure get established at the interference. So this whole thing is going to give you the net pressure. If we integrate this pressure over this area, we are going to get some net force like this. Okay? The net radial force will be acting at the interface like this. This is a net radial force. Now there is a friction. There is a friction between the shaft and the pulley interface, which is having a value of mu. Now what happens when this joint try to slide each other? There will be a tangential force which gets generated, which is going to be mu times the radial force. Okay, this is the tangential force. This tangential force will be acting at every point in that interference radius. This is radial force. This whole thing is a tangential force. This tangential force times this radius is the torque this joint can take. Once the torque that the belt is transmitting exceeds this torque, then the joint is going to slip. To handle this problem, there are well-established formulas available in the literature. If there is a interference between two cylinders, what is going to be the maximum pressure and the pressure times multiplied this area is the force, the radial force that I was talking about. The radial force times mu is the tangential force. The tangential force times the radius is the torque this joint can take. Now, it's relatively easy to calculate how much is the interference that you need to withstand certain amount of torque. But in plastics, let's say this is a time and this is this pressure, the contact pressure, this contact pressure. This contact pressure relaxes over time because of the creeping phenomena that happens in the material. So when this pressure comes down, eventually the radial force is going to come down and the tangential force is going to come down, and hence the torque is also going to come down. Okay, so we are going to predict how much torque it is going to lose over time due to the creeping of the plastic material, so that we can increase the initial pressure, we should make sure pressure or torque after, let's say, 10,000 hours is more than the torque which is transmitted by the belt, which is operating torque. Okay. So if the behavior is like this, something like this, okay, then what's going to happen? Probably after 4,000 hours of operation, the joint is going to slip. Okay, so we want to predict that. Let's assume this is the model that we are going to deal with, representative model. The first thing is, this is of this particular material. It's a Wardell, and this is supplied by this particular supplier. Let's look at the spec sheet of this particular supplier. This is the spec sheet from this particular supplier. Okay, so when we look at these details, it talks about the various chemical composition and so on. We are interested in the mechanical aspects of it. Okay, so what we are looking at is, this is our product. We are looking at basically here, when we do the interference fit, it's mostly, the material is mostly undergoing compression rather than tension. So this particular material is assumed to have different stress strain curve in tension, and the stress strain curve in the compression looks different. Okay, because the way you look at it, the Young's modulus in tension is around 2.65, and the same the Young's modulus in compression is 2.68. And also, if you look at the compressive strength is 100 MPa, but whereas the tensile strength is 83 MPa. For time being, we assume that the material is having the same yield in tension and compression. The stress strain curve is exactly same in tension and compression. Okay, though we can handle different stress strain curves, but just to explain the process, I'm assuming the material is behaving same in tension and compression. Okay, because of the interference fit, the material is expected to undergo some plastic. This is the typical stress strain curve of this particular material. So this is expected to undergo kind of a nonlinear curve. It's not in a linear region. Okay, that's one thing. The other thing we are looking at is the creep. So let's look at, we have a creep information given in the spec sheet at page number 22. Let's go page number 22 and look at this. This is the creep modulus for Wardell 201. This data is given at two temperatures. This is at 23 degrees Celsius and 85 degrees Celsius. The data are measured at around 20.7 megapascal stress limit. Okay, so we have this data. Now, we know that this supplier is having this particular data. We can talk to the supplier and get this information. In case if we don't have the data, if you have the curves, it is possible to digitize this one. I have taken the stress strain curve from the PDF file that you're seeing, and I could digitize this data using some free software that's available in internet. I have used Engage Digitizer. You can get all this information. All the information is going to be available here. So now basically what it talks about is the percentage of strain and the stress in Pascal. I assume this is basically engineering strain and engineering stress. Okay. So this is the digitized data. The stress in KPI, kilo PSI, and the strain percentage. So we're converting this percentage of strain into the actual percentage by dividing by 100. And this is the stress. It's an engineering stress in KPSI. This is converted into megapascal by using the conversion factor between kilo PSI to MPa. So now we basically have the engineering stress strain curve in strain versus MPa stress. Now To use any nonlinear plasticity data in ANSYS, the stress strain input to the software should be in terms of true strain and true stress. So we do have a relationship between true stress and engineering stress, and we can also convert the engineering strain into a true strain. First, what I'm doing is I'm converting my engineering strain into true strain, and then similarly we can convert using the engineering stress and engineering strain, we can get the true strain. Okay, so we got this information here. This is the final stress strain curve that we are going to use. Okay, so I have plotted this final stress strain curve, true stress strain curve here. The second task is to find out the elastic modulus or the Young's modulus for this material, which we typically take up to the range where the stress strain curve is kind of a linear. So when I draw a plot, approximately up to this point, this becomes linear. This is around 13. The stress is around 13.065. So the Young's modulus is stress by strain. This is my my Young's modulus. It's approximately 2619. The value given in the spec sheet. So 2680 is the value given in the spec sheet. We get 2618. This is kind of approximately okay. We can go ahead with this because there is a difference in terms of the secant and the tangent modulus. Okay, I'm not getting into the details of this, but the point I want to say here is the value that we calculated from the stress strain curve and the value that is given as per ASTM stress standard are almost the same. Okay, that's the point I'm trying to make. Then, to feed the stress strain curve into ANSYS, we need to convert the total strain into only plastic strain. So up to this is basically our yield point now. So up to the yield point, the plastic strain is 0, and this becomes our yield stress. Then, if you want only the plastic strain, so the plastic strain is nothing but total strain minus the elastic strain. Okay, so elastic strain is nothing but stress by Young's modulus. The stress by Young's modulus is our elastic strain. So if we subtract from total strain only the elastic strain, we are going to get only the plastic strain. So this is true plastic strain versus the stress strain curve. Okay. So once I have this information, what we are going to do is that we are going to feed this information into ANSYS. Okay, so if we go to this engineering data, this is my Verdal material. For this, I'm going to input my Young's modulus. This is 2619 that we calculated, and Poisson ratio is 0.42. And this is my plastic strain versus stress that we calculated here. This data is fed in here. Okay, so now we got the stress strain part of it, which will capture the initial behavior. The second part is the time dependent behavior, which is the creep behavior. For that, we have a creep information given in page 22, I believe. That's where we have got the, yeah. So we have this information. The information here is given in a log scale. The time axis in a log scale because we are talking really about very long duration. And the creep modulus is given. Okay. Now let's look at this data. So what I have done is that we have actually we can talk to the supplier and get the data for this particular graph. Okay, so here, for example, I have got the data given here. This is basically time versus the creep modulus. Okay, we have got the data here. Now, if we go and plot this data, so this is in a linear scale. If we look at this data in a log scale, it will look like what we have in the graph. Okay, basically. So this is in a linear scale x-axis. Okay. Another point to notice is that this creep modulus given under stress of 3000 psi at the temperature of 23 degrees Celsius. Now we are dealing with MPa unit system. Okay, so we need to convert the stress into MPa unit system. Temperature remains same, and also the creep modulus is given in KSI. We need to convert this into a MPa. Okay, so now we have, for different time, we have a creep modulus. But basically, to use the creep data in ANSYS, we need time versus the creep strain, not the creep modulus. So it is possible to calculate the creep strain from modulus, because we know that modulus is nothing but the stress and strain. If you want to calculate the strain is nothing but stress by modulus. So in this case, we know the stress limit at which this test is done is under 2.6 MPa stress. So we know the stress, we know the modulus at different times. So eventually what we can do is that we can calculate time versus strain. So for example here, I'm interested only up to 10,000 hours. So finally we have got a curve like this. This is my time axis, this is my creep strain axis. Okay. Now let's look at the shape of this data. The data looks like this. If you are familiar a little bit with the basics of the creep, there are three regions of creep. One is the primary creep and the secondary creep. Then it extends like this. This goes into a tertiary creep. So looking at this data, there is a huge amount of creep strain that happens at the initial stage here. After this point, the creep, say probably up to this region, there is a huge increment of creep strain. After this, the increment is very small in the secondary creep region. So basically, we need to analyze this data in a, consider this as a primary creep for our analysis purpose. Okay. If you want, then we need to look at what are the various creep models available in ANSYS. So if you go to ANSYS help manual and search for creep, we can find some information about creep. There are approximately 13 different creep models available in ANSYS, and further user can define their own creep law. Now we are interested in the primary. So these are all the creep models which is applicable for a primary creep. And now we know that there are certain creep models which talks about creep strain rate as a function of time. Okay, so if you look at these things, there is this dot really refers to a creep strain rate. There are some models which talks about the creep strain, not the particular modified time hardening model. So the equation for the modified time hardening model looks like this. This is the equation for modified time hardening model. Now let's try to understand a little bit. We need to understand a little bit of graphing and the hyperbolas or the parabolas or the exponential curves and so on. Let's look at this equation. What it says. The creep strain is function of stress, time, and temperature. Okay, there are three variables: stress sigma, time t, and temperature capital T. So here, this pulley is going to operate at room temperature. It's not at elevated temperature. It's at 23 degrees Celsius. Now, what we are going to in this material, the temperature is always constant. So what we are going to say, since we have the creep strain data for only one temperature, the function of temperature is not there in this particular case. So this whole term is going to be not varying with time. This is going to be 1, this whole exponential term. So I can make this C4 as 0 in this whole thing so that I eliminate the temperature dependence. Then there are now end with 3 constants. One is C1. C1 is a global scale factor. C2 is the stress exponent and C3 is the time exponent. Okay, now let's look at. For every time, we can write this equation. So for example, I'm just coding this equation. Okay, basically this is nothing but C1 times the stress times C2 constant. I'm assuming some value, let's say, multiplied by time times the C3 plus 1 and so on. Okay, and exponential of this term divided by C3 plus 1. Now, it is possible for calculate this for every time. So we are going to our warranty for this product is approximately 1 lakh hours or 100,000 hours. So we are going to calculate up to that. Okay, so we calculate this curve. Now, when you are changing anything, you need to little bit understand. C is the overall global factor. Look at this curve. With these constants, we are going to match. This is our experimental data and the curve fitted data. Say, for example, if I am just changing my, let's say this is 0 instead of 7. If I put 8, the entire curve is going to be shifted up. Okay, you need to understand little bit of how these constants are going to change the shape of the curve. Okay, so for example, C2 is the stress exponent. So for example, if you change the C2, again it's going to shift the origin itself, not only the shape. Okay, this is about C2. The third one is, this is the power of time. Now if you look at, as the time increases, the rate in which the creep strain increases is reducing. Okay, see here, at initial time, as the time increases, the creep strain is very sharply jumping. But if you go towards the later time, the amount of increase in the creep strain for the same duration of time is relatively less. This means that this term has to be something like this C3 has to be minus. Okay, so let's look at this term. Instead of 9, let's say if I put 5. Okay, so you will get the different way. So you need to understand this equation a little bit and play around this until you get the match between the experimental data and this. The other way to do this is ANSYS can do the curve fit for this particular data. I will also explain that. In this case, we have a time axis. Time axis is we have a time and the creep strain data. I'm going to get the data into this particular text file. This is basically nothing but the first column, and the strain is nothing but this information, and I'm going to supply. This is the syntax you need to follow. /1 means the first column refers to time. /2 means the second column refers to creep strain. And the stress, equivalent stress or 1 measure stress for this data is 27 because this sigma is needed here. Okay, we need to supply this one. And the temperature is 22. Okay, we are solving for this. Let me. Okay, so we have this data. This data is to a local hard disk. Now let's go to, unfortunately, as of today, in June 2019, we can't do this curve fitting in ANSYS workbench environment. We have to use ANSYS mechanical APDL environment. Okay, I'm just going to a mechanical APDL environment, pre-processing, material models, structural, nonlinear, inelastic. This is a rate-dependent material, and I'm just using creep. I'm just going to do a creep curve fitting. Okay. Here we can enter the data, or we can load the data from a particular file. This data is in my desktop, Delhi Creep. This is the file where I have saved the information. What this is going to do is it's going to bring the time, because we mentioned the first column is time, and the second column is a creep strain. The syntax for creep strain is CREQ. And the equivalent stress is 27, temperature is 22. Okay. Then next, it's going to bring up here. We have various creep models. We are under primary creep and modified time hardening. Okay. And you can say this C4 is 0. I don't want to iterate it. You can fix it and say solve. Okay. So the solution is complete. It is going to calculate those constants. Okay. So if you look at the constant that we have done analytically, and this is, for example, C3 is something like 0.9 e power 4, or in fact we can use this data also and see there may be a multiple possibilities. Let me just try this out. We keep this aside. Let me bring this data. Okay, let me do one thing. Okay, now we can go and plot this graph. You can see this is the experimental data and modified. They match well, and they are very nice. Okay, from this way also we can do that. So once you are happy with this, just say save and close. So this has brought these constants here. Let me copy these constants and put it here. Let's see with these constants how the curve going to look like. Okay, now because this is kind of a curve fitting, and there may be more than one possibility of values for which it will match well. Okay, but it is important that we understand what this equation means, what is the influence of the physical behavior of each of these constants. Okay. So there are multiple ways you can use ANSYS curve fitting, or you could do your own curve fitting by doing a calendar and so on. Okay. Having done this, now we need to feed in this data. What we can do for this particular material, we can choose the modified time hardening, drag and drop, and then it will ask for the constants. Okay, we have to provide the constant. So one thing you have to make sure is the stress unit used here is Newton per mm squared, MPa. So you have to use the unit system here. And another point I want to really point out is that here the time unit is hours. Okay, so here we don't have a time choice of hour units. We always go with seconds. But later in mechanics, when we are setting the duration for the analysis, the duration also we should enter in terms of hours, not in terms of seconds. Actually, we haven't converted the hours into seconds. So this is kind of a pseudo unit system. This seconds for the time should be interpreted as hours for all practical purposes. Okay. Now let's look at the analysis setup. By the way, this is the new ANSYS 2019 R2 GUI. It has a very nice features. Let's look at this. So basically, this is a plastic housing. which is made up of Wardell material, and this is the steel shaft. It's made up of structural steel. And if we look at the material, I haven't really modeled any interference as such between the component, but instead the interference is given in terms of the contact offset. So initially I'm starting with 0.1 mm offset. Then what I'm doing is that this shaft is fixed. We are just resolving the interference fit, and the bottom is sitting on a kind of a table or a plane. So this bottom face of the bush or the gear cannot move along the y direction, okay, in the out of plane. That's what it means. But there is no other constraint because the OD is the place where the pulley is running. So this is free to expand, or as we are resolving the interference, when we are trying to push the shaft inside, the OD of this gear is allowed to expand, okay? So we cannot constrain that. But other possibility is that this is a symmetric. What it means in the sense, when you are pushing this line, all the material along this particular line is not going to move along the z-axis, okay? So we can take these two lines and constrain this in x-axis. So this portion of the material is not going to move along z-axis. And same way, this two, all the material along this line is not going to move along z-axis. It's basically a symmetric constraint is used. Okay, this is about the support. Coming to the analysis settings, we need to solve this in two steps. The first step is to establish the initial stress state for the creep. For the creep to happen, there should be certain amount of initial stress in the material. Okay, so we need to establish. In the first load step, it is just solved for small time. There is no other external load applied. Okay, only the interference is what we are trying to study. How the interference is going to get loosened over the time. So here, in the first load step, the creep effect is turned off. Okay. In the second load step, as you can see, the creep effect is turned on, and we are solving it for 100,000 hours. Though this says unit a second, as I explained earlier, this is a static problem. There is no inertial effect, or the velocity or acceleration is not playing any role. So whatever the time we are using here is kind of a pseudo time. Though this says as a second, it should be interpreted as 100,000 hours. Okay, we are solving in number of substeps and so on. So I have solved this problem. Now let's look at the total deformation. I'm looking at the end of the first load step. This is after resolving the contact interference. Okay, we can go and look at the contact pressure at 1 second. This is how the contact pressure distribution is. Okay. Now, if you look at this, let me set this as a reset all. Okay, the maximum pressure, as you can see in this graph, it is around 24.7, but over the time this just drops. Okay, so initially it is 0, then it's gone up to 29 during the initial interference, and then it's coming down. Okay, we can look at the contact pressure distribution at any point of time, and we can look at how it is changing. Also, what we can do is that we can look at the radial force. We can insert a probe, force reaction probe. That is what is this, and we are looking at the contact region. Contact region corresponds to this contact region, and we need a radial force in the cylindrical coordinate system. A cylindrical coordinate system is created at the center of this thing. I'm looking at the reaction force in this particular cylindrical coordinate system. Here so because of the interference fit, it's going to only produce the pressure multiplied by this particular area is, if we hide this, multiplied by this particular whole area is going to give us the radial force. Okay, this much is the radial force. As we can see, the radial force initially is this much and it is coming down over time. Okay, now we know, and also the beauty, you notice that we haven't used any friction here. Okay, really we don't want to use that. If we use friction, then numerically the problem is going to be very complex. Even without using the friction, it is possible to estimate the torque. Okay, so let me copy the time versus the radial force. This is my time in hours basically, and this is my F normal force in newtons. Okay, now I want the tangential force in newton. My mu, the friction coefficient, let's say it's 0.35. So this is nothing but 0.35 into the normal force. This much is my normal force. Now let's say the approximate radius of this interference. Okay, this is the radius is 20 mm is the radius. I'm assuming this whole thing is a circle, rather considering the geometry. Even we could do that, just for a simplicity I will assume that. Okay, my radius is 20 is my, okay, is 20 the radius or diameter? Let me say that it's a radius. Okay, as you can see the radius is 20 mm, so 20 mm is my radius. So my torque or resisting torque, this is going to be in the units of Newton mm. So this is going to be my tangential force times the radius. Radius is kind of fixed. Okay, now we can plot time versus resisting torque on a graph, which is going to look like this. Okay, so let me remove this up to one time. Okay, so initially my torque is, the joint torque is around 107 kilonewton mm, but over time it has come down drastically. Okay, so the total reduction, I think I have to use from here basically, not from there. Okay, this is the initial torque. When we just assemble this much is the torque, and after 100,000 hours we have lost the torque capacity of approximately 20,000 Newton mm. Okay, so let's say the belt is, if the belt is expected to transmit the torque of let's say around 95,000 over the time, then this design is safe. We can say that, okay, the 0.1 mm interference that we have used for this material is really good enough. Okay, it can really stand and do that. If the belt for this design is expected to transmit something like this, say for example 11, let's say this is a operating torque is this much, and initial resisting torque, the initial resisting torque we have is this much. Okay, now let's look at how much is the margin we have. So we have a margin. Okay, let's say 1 minus, sorry, this would be minus 1. Okay, let's say we have a 12% margin, but what happens after margin? Let's look at this is resisting torque at let's say 1 lakh hours. Now is this much. Now if we check the margin, this is my operating torque divided by resisting torque minus 1. We really lost, it's in a minus. So it means the joint is going to really slip. So if you want to design this for that, either we have to increase the initial interference such that this point goes up initially, so that even after 10,000 hours it's not going to drop down, or we could reduce the stress levels. Say, let's look at this model. Let's look at the equivalent stress at let's look at the equivalent stress at the initial time. It's around 26 MPa. And another important point, I think it's worth highlighting this. Okay, now look at 20.6 MPa. They are matching. If the stress levels are coming down, let's say from 20.6 to 15, now that particular node will obey this particular stress strain curve. Okay, not this, not stress strain curve, the time versus creep curve. If the stress goes up something instead of 20.6, if it goes to 30, this is the behavior. It is this is how the creep strain will increase for a certain increment of time. Okay, this is something you need to be very careful, because we need to look at the stress levels at the initial time after establishing the interference. So whatever the stress level we are seeing and whatever the creep curve that we are using, it should be kind of close. Okay, there should not be a much difference between those two, because we don't know if the stress level goes up when we actually do a testing. It is not necessary that it has to follow the same stress strain curve. Say, for example, at 20, it is following a curve like this. This is around 20 MPa. Probably when we do it at 50 MPa, the curve may be something different like this, not necessarily like this. It might have behaved like this at probably 100 MPa or what it is. Okay, we need to really do this testing and get the data at least less than the maximum stress that we are going to see in the component during the initial assembly. That's another piece of information that you need to consider while collecting the creep test data to do this kind of analysis. Okay, hope this gives you some idea about how to really do a finite element based simulation assessment of the joint capacity, either for a push out load or a torque for a plastic assembly which involves interference fit and the creep relaxation effect. Okay, as you see, it's important that we should have sufficient material data to do this kind of assessment. Okay, either you should be able to test it yourself in your testing lab, or you should establish a good supplier whom can test and provide these kind of data. Okay, hope you. It is very important that without we having the correct stress strain curve, see sometimes this material has undergone some amount of plastic strain also. Okay, as you can see at the there is some kind of a bulk yielding here and the local yielding here. So do this kind of this portion is not going to come back after you remove the shaft. There will be a ovality in the shaft in the pulley hub because of these plastic strain. Okay, if you like to, you may like to limit the stresses within the yield stress of the material as well. For that purpose, to assess the plastic strains in the material, we should have access to the stress strain curve as well. Okay.
That's okay, not a problem. That you can just change it. And the second thing is, see, whatever I'm having a stress strain curve, right? That is the engineering stress strain curve. So engineering stress strain curve I'm converted to stress strain curve. So from there, why do I convert to plastic strain? Because whatever I'm getting after the yield stress and or yield strain, it's basically a plastic data. So that plastic data I'm already having it in true strain.
No, if you have the engineering, the stress strain curve, this is a strain and the stress. Okay, so up to this point, if you load it and unload it, you will come back to 0. Okay, but suppose say if you have loaded the material up to here, let's say this is the Young's modulus curve. Up to this point, this is the total. Okay, let me again. Okay, this is the stress at a particular instant. Okay, this is the strain, total strain at that particular instant, corresponding to that stress.
Which is elastic strain plus plastic strain.
This portion is elastic.
Yeah.
This portion is plastic. Okay, so you cannot say the strain that corresponds to a particular stress is totally plastic. There is a component of elastic. You need to subtract that component.
Okay.
So this is nothing but this stress divided by this is nothing but your Young's modulus. Okay, this E and this E is going to be the same. Okay, the elastic strain will be the stress by the Young's modulus.
Yeah, that is fine.
That's why we are doing this operation. Okay.
So now what we have considered is for primary creep, right? That's an assumption where the failure happens maximum. So we are considering primary creep. Will it be the same for secondary creep and tertiary creep also? So can I use a similar formula? I hope yes. It is.
You can't do a ternary creep because that material will become highly unstable. We can't numerically. You can't numerically do anything about this region, okay? Because with a small time it will lead to a failure and all. But secondary creep, there are different creep laws, so you can use that, okay? So the process will remain same, okay? You have to use any one of these equations to model them.
Okay.
Okay, so another example that I have given is, I think it's a Norton creep law, okay? This is common. What it is, but the process is almost the same.
Okay, and the other question is, no matter whatever modeling I use it, maybe it is a time hardening or Norton or strain hardening, so I have to do the curve fitting, right? That's mandatory.
Yes, see basically.
In order to derive the constants.
Yes, these constants are important because when you write the constitutive law, all these constant is what software require. See, finally, when we are feeding this information here, we are saying what is the law? once you choose what law you want to use, it will ask all these constants.
Yeah.
Okay, where is this constants? These constants you have to provide. So one way is that we can do this curve fitting inside ANSYS. At least for creep curve fitting, our ANSYS is very good. Otherwise, we can use some external tool, or you can use Excel itself to do all these things.
Okay, is it possible to do it in Workbench only? The curve
no,
fitting?
Workbench it is not possible.
2019 is not possible.
Not possible, yeah.
See, now we are not using temperature dependent, right? So that's where we thought we have removed that C4 constant because temperature we consider to be at room temperature, so temperature is not changing. But in my case, the temperature could be at ambient, right? I mean, whatever the environmental temperature.
Yeah, it's sometimes 22 degrees Celsius.
Yeah, so that's like sort of an assumption for us, right?
Yeah, but you can generate multiple curves at multiple temperature. Okay, say for example, I have one data like this. Okay, you can produce one more thing at, let's say, 50 degrees Celsius, one more data. Okay, and one more data at say something like 200 degrees Celsius. Let's say file save as, let's say quick fit, let's say 200 CR, whatever it is. Okay, you can add another data set.
Now say if I have a Young's modulus of say 4000 MPa at room temperature, for example, and if I'm heating it to say 100 degrees centigrade, my Young's modulus will go less, maybe 1500 MPa. So similarly, similarly, we have to generate time with respect to creep stress. I mean, in turn, when I do a conversion to creep strain, I need that data from the supplier.
Yes, you need, see, this case, since it is operating at one temperature, we have used only one temperature, but usually the testings are done at various temperature. The curve will be different. Okay, so these data you have to use it. Okay, so if you have multiple data, you can add one data, then you can add like this. Okay, multiple data are given at various temperatures. Get that data, do the following same conversion and put it in different file for different temperatures like this. You can add another set, add a data set. It will ask you to browse for that file. Okay, you can browse this file. This is for 50. Eventually, you are going to have a different data here. Okay, then you can go next, but this time this is not going to be 0.
Yeah, correct. That's automatic.
Okay, now. Yeah, so now you have to find what should be the constant for that. Then you can solve it. Okay, sometimes see, this is a curve fitting. Sometimes you have to assume there is no temperature variance, find some initial values for this, then you change this. You have to unfix this, so that keeping this as providing initial value is important for any curve fitting tool. Okay. See, now, since in this case I have both the data exactly same, experimental data 1 and experimental for both the two temperature I have used exactly same data. If you have a different data, it will show 4 different curves. Okay, so the experimental data 1, experimental data 2, curve fitted data for 1 temperature and 2 temperature and so on.
We are almost done. Let me summarize what we have done so far. We have taken a plastic pulley press fitted over a shaft to transmit certain amount of torque through belt system, and we have gone through the entire process of selecting the material data, selecting creep law, curve fitting, analysis setting for the creep requirements, result interpretation, and how to make design decisions. Though we have gone through all the stages of this process for a typical plastic pulley assembly, the same concept is equally applicable for many different plastic assemblies. such as snap fit products that you are seeing on the screen and the gear mechanisms, etc. If you looked at this video very carefully, we have spent relatively little time on ANSYS as a FEA analysis tool. We have spent most of the time in collecting the data those are required for ANSYS to carry out any calculation. This is where the engineering knowledge comes into picture. Even we are dealing with a very complicated assembly having millions of nodes and so many contacts, etc. The complexity of the model is taken care by ANSYS as a software and the hardware computing capacity. But the critical part is providing the input to ANSYS software and looking at the input and making some practical inferences and take design decisions. We need to really simplify the model to an extent where the numerical computation becomes relatively simple, but care should be taken the simplification we are making do not compromise anything on the physics of the problem. Thinking about applying a friction coefficient in this contact and applying a torque as an external load and see how the stress or strain develops in the model, yes, can be done. It looks fancy, but to make any design decisions, those are all really not required. Okay. Many of the time, to make any practical decisions, we can simplify even a very sophisticated analysis to a minimal extent, where we can apply the basic engineering concept on the very basic information that we get from analysis tools, then using the well-established formulas that has been followed by industry for the centuries to derive useful design parameters such as torque capacity and make useful design decisions. Okay, and for doing this kind of analysis, having required material data is very important. If we do not have stress strain curve or a creep information for this particular material that you are dealing with, it is almost not possible to carry out this kind of analysis. Yes, we can carry out analysis assuming some material constant, but the question is how sure in using those design parameters to make practical design decision. In turn, this may have a very big impact or consequence on the cost and brand of the company, as this directly impacts warranty life that is given to the consumers of this product. Okay, so we should have a good in-house testing lab or kind of a collaboration with a testing agency, or a good reputed material supplier who can provide all the required data to carry out various type of analysis which are relevant to the product that we are designing. Again, I insist, it is important to have the correct material data for the particular material by which the product is manufactured. Okay. I hope this video is really helpful. There may be some mistakes. If you have any comments or feedback, please feel free to give your comments and feedbacks in the comment section. Thank you very much.